During live demonstrations, mathematicians compute complex arithmetic in real time, arriving at the correct answer faster than an audience member can type the numbers. At the upper limits of human capacity, competitive calculators can process 15 separate three-digit numbers in under 2 seconds. The underlying mechanism for many of these individuals is the mental abacus. The training begins with a physical tool, manipulating sliding beads across rigid rods to perform math. Over years of practice, experts discard the physical device. They retain a persistent, interactive representation of the abacus in their mind, moving imaginary beads. These calculation speeds exceed the established throughput of standard verbal working memory. To process numbers at this rate, the brain must utilize a different processing architecture. Standard verbal logic processing operates as a low bandwidth channel. Humans can typically hold only a few distinct pieces of auditory information before reaching capacity. By comparison, the brain's visual and spatial centers are high-volume, simultaneous processors. They are designed to parse environmental data, tracking depth and geometry in real time. Electroencephalography confirms the structural shift. In studies of mental abacus users, intense activity is localized in the right hemisphere's visual cortex. Meanwhile, regions associated with verbal arithmetic show lower activation. These subjects shift numerical tasks away from language centers, manipulating a spatial object. This suggests extreme mathematical fluency is achieved by routing numerical data through visual and spatial pathways. To verify this, we must map the physiological cost of hearing a number versus seeing one. To measure the biological cost of thinking, researchers track pupillometry, fluctuations in pupil diameter that act as a proxy for cognitive effort. A study conducted by Klemer, Tversky, and Hanaran was designed to test the specific biological cost of hearing numbers versus seeing them across a variety of tasks. The experiment required strict controls to eliminate the pupillary light reflex. Both aural and visual conditions were matched on brightness, using isoluminant gray backgrounds and placeholder masks to prevent the pupil from reacting to sudden changes in light. Motor controls were also implemented. Visual stimuli were restricted to a fixed area in the center of the screen, ensuring participants kept their gaze stationary to avoid saccade-induced data corruption. By neutralizing both light and movement variables, the researchers isolated the cognitive component. Any difference in pupil dilation between audio and visual tasks represents a difference in the mental effort required. In the first task, subjects solved identical mental multiplication problems, presented either purely orally through speakers or purely visually on a screen. This chart graphs the resulting pupillary response. The x-axis represents time, mapping the moments the subjects received each number. The y-axis tracks the magnitude of pupil dilation in millimeters. Both aural and visual tasks trigger the same cognitive trajectory over time, rising and falling in sync with the presentation of the numbers. But there is a distinct gap in magnitude. The aural presentation required a 0.35 millimeter dilation, more than double the 0.16 millimeters measured for the visual task. This increase in biological effort correlates with performance outcomes. Participants made significantly more errors during the high-load aural presentation.
Solving arithmetic visually appears to be physiologically cheaper. The brain requires less physical energy to process seen numbers than heard numbers. To understand why visual processing is more efficient, the researchers tested a digit-span memory task, which isolates data retention from active calculation. This graph maps pupil dilation as subjects memorize ascending sequences of numbers. The length of the sequence dictates the height of the curve. The lines plateau at the higher sequence lengths, representing the absolute maximum capacity of human working memory. At that maximum sequence length, there is a gap of nearly 0.2 millimeters. This shows the persistent energy cost of holding audio in memory compared to visual data. Auditory memory retention operates as an active, energy-draining loop. Visual persistence, however, allows the brain to passively store the same data. This mechanical difference maps onto Alan Badley's model of working memory. Verbal and aural systems run through the articulatory loop. When a subject hears a math problem, this channel reaches capacity.
The articulatory loop must simultaneously hold the numbers in memory while also executing the mathematical operations. This creates the high cognitive load seen in the pupil data. Memory has a parallel system, the visuospatial sketchpad. Visual presentation allows for dual coding. The brain delegates the memory requirement to the visuospatial sketchpad, clearing space within the articulatory loop. Visual presentation lowers cognitive load because it offloads the memory requirement to the spatial system, allowing the verbal system to focus on calculation. We see this efficiency in real-time arithmetic, but spatial routing is also involved in the initial acquisition of mathematical concepts. Researchers measure spatial reasoning through mental rotation tasks, testing the ability to manipulate objects in three-dimensional space. A 2019 study mapped students' mental rotation skills against their math performance. For already mastered operations like addition and subtraction, spatial skills offered no predictive advantage. But for newly acquired concepts like multiplication and division, there was a clear predictive link. This data supports the spatial scaffolding hypothesis. Before children can manipulate abstract symbolic quantities verbally, they must map those concepts onto a mental member line. Spatial skills provide the foundational scaffolding for building mathematical architecture. They allow the brain to organize abstract concepts during the early stages of learning. This brings us back to the mental abacus users computing equations at speeds that exceed verbal processing limits. These expert practitioners have optimized both dual coding and spatial scaffolding. By converting numbers into beads on an imaginary device, they perform calculations within the high-bandwidth visual spatial sketchpad, bypassing the articulatory loop. These performers have achieved their speed by rerouting cognitive data through a biologically efficient physiological pathway. This architecture has implications for both educational design and human-computer interaction. Optimizing how we display visual data is a matter of exploiting the brain's biological energy limits to reduce cognitive load. The modality of information, how we see a number versus how we hear that same number, ultimately determines the physiological cost of thinking.